Your M1 moments questions will sometimes include objects which are on the point of tipping, and I'm going to try to show you what that means today using this equipment here that we've borrowed from the science lab. So I've got a meter ruler here, which will be our horizontal beam. I've got two supports, two wooden blocks which will act as supports. I've got some masses that we can add. And I've also got two balances so that we can try to measure the reaction force which is produced by the supports on the beam. So first thing I'm going to do is just check the mass of this meter ruler as accurately as I can. About 102.7 there. So if I can split it across these two balances, we'd expect it to be about 51 grams on each. Before I do that, I'm going to place the supports on the balances. I want the ruler to rest on the supports rather than the balances itself, and I want these balances to tell me the mass of the ruler, not the mass of the supports. So I'm just going to zero those again. Okay, and now if I put the ruler on, let's just get these lined up a bit better, I should be able to get it to rest so that we've got about 51 grams on each. Let's see if I can do that. I won't get it perfectly, but I'll try. So I've got 51.203 here, 51.6 there, that's as close as I'm going to get. Okay, now it's worth pointing out, I suppose, that these balances are obviously reading in grams, not newtons. So I'm measuring in grams rather than measuring the force directly. One of them does have the option to switch to newtons, but the other one doesn't. So to avoid the confusion of having two different units, I'm going to stick to grams. You know that you can turn grams to kilograms and then multiply by 9.8 to convert to newtons. So the patterns we see measuring in grams should be exactly the same as we would see if we were measuring in newtons. Okay, I've got my ruler set up on the two supports. The reading here actually is telling me the force that's pressing down on the balance. That's how a balance works. But by Newton's third law, that is also the force that is pressing up from the support onto the ruler. So I am measuring here the reaction force in grams on the ruler. Okay, now I'm going to add a mass here. This is a 50 gram mass, and I'm going to place it in the centre of this ruler, as close as I can get to the centre. Of course, the reaction force on both of these supports will have to increase to account for the mass that I've just added. If I get it right in the middle, they would increase by the same amount. I haven't got it right in the middle, but you can see that the reaction force on both of those has increased. And of course, that's because in equilibrium, the total downwards force, in other words, the weight of the ruler and the weight of the mass, must be balanced by the total upwards force. That is the sum of the two reaction forces here. So if I add more mass, we should see again more reaction force. Okay, that's quite straightforward, I think. Now, I'm going to move this mass closer to one balance than the other. And I want you to watch how that affects the numbers. So without the mass, they're both on around about 51. With the mass, this one has gone up to 94.5. This one has only gone up to 58 point something. Of course, you would probably expect that. I've put most of the extra force close to this balance. So this reaction force, this support is going to have to bear more of that, and the reaction force here will increase much more. Similarly, if I put the mass down at this end, this reaction force will increase much more than this one. Okay, now I'm going to remove it again, and I want you to watch what happens to this balance if I place the mass this side of the other balance. Yeah? So I'm putting it on the other side of the support, and I want you to watch what happens to this number here. It actually goes down. Okay, and I'm going to slide this mass further along and continue to watch what happens to that number on the other side. Now, these two readings should still add up to the same amount, because the total upwards force from these two supports should still be exactly equal to the total downwards force produced by the weight of the ruler and the weight of the mass. But as I move the position of the mass, the way in which that force is shared between these two supports is different. And the further I move it in this direction, the more this number is reducing, this force is reducing, and this one is increasing. So move it further and further. What do you think happens when this reading gets to 0? Move that out of the way, I'm going to knock it over. So I'm down to 2.3 or 4 there. There it goes. Okay, so when this reading goes to 0, that is the point at which the ruler will start to tip in this direction. That is what we need to remember when we're being asked about tipping point. So if you have a question where you've got, for example, this thing in equilibrium, and a man stands on it and starts to walk along the beam, how far can he get before the beam starts to tip? Well, that's what you need to remember. At the point where the beam is going to tip, this reaction force will be 0, and that's what you would use in your calculation. It makes sense, because if you think as soon as this starts to tip, there is no longer any contact here, therefore there cannot be a force pushing upwards there. Now, there's another variation on this kind of question, which can say, you've got your beam in equilibrium, everything's balanced, and then you add a mass somewhere on the beam. And you might be asked something like, what's the maximum mass you can add here before it starts to tip? So I can try adding masses in the same way, and you will see this reading decrease. And as before, when it gets to 0, the ruler will tip. Now, I'm not going to be able to do it exactly this time because my masses go up in lumps of 50 grams. And it's very unlikely to be an exact multiple of 50 grams that is going to cause tipping here. I suspect that this next mass will be enough to do it. Yeah. So the reaction force there with 2 masses on it is reading, oh, it's very close to tipping there anyway. It's 0.42. I've almost got it tipped there. So any slight mass increase there is going to take that down below 0. Cause it to tip. Sometimes the word tilting or tipping is not mentioned in the question, and sometimes you are just asked something about, if the rod is to remain in equilibrium, what's the maximum mass I can place at a certain point? And you have to remember that that means what's the maximum I can place there before this starts to tip. Or you might be asked the thing about moving an object or moving a person along the beam. What's the furthest a person can walk along this beam and it still stay in equilibrium? Again, you're looking for how far can he walk before it starts to tilt. And you need to remember that one of these forces is going to go to 0 when it starts to tilt. Now, the other variation on this, or the other way it can be asked, is of course, if you don't have 2 supports, but you have something hanging on 2 strings. So imagine that this ruler was hanging on 2 strings. When it starts to tip, the tension in this one is going to go to 0, the string will go slack, and it'll be a tension rather than a reaction force that goes to 0. But otherwise, the principle is the same.